Welcome back to the deep dive. We're your shortcut to staying genuinely informed in this incredibly fast-moving world of AI.
Absolutely. If you're watching the large language model space, new papers, new breakthroughs, it feels like they land almost every single day.
It's a lot. It really is. It's kind of a whirlwind of research, and honestly, it's easy to feel a bit lost in just the sheer volume of it all.
Mm-hmm.
But today, we're going to try and cut through that noise. We want to bring you the core insights from one paper that's, well, making some serious waves.
Exactly. So our mission today is to really unpack Falcon-H1, a family of hybrid head language models redefining efficiency and performance.
Okay.
We're doing a proper deep dive into this novel series of LLMs. We'll explore their, frankly, innovative architecture, the really meticulous training strategies they used, and maybe most importantly, the technical implications of what they've actually managed to achieve. So by the end of this, you should walk away with a pretty clear understanding of how these models are aiming for state-of-the-art performance, but with, really remarkable efficiency. And they challenge some long-held assumptions about AI scaling along the way.
That's exactly what we like to hear. So, okay, what can you expect from this deep dive?
Well, we're going to explore how Falcon-H1 manages to blend the strengths of different AI architectures.
Yeah.
It leads to some pretty surprising results, actually.
Interesting.
Then we'll get into the nitty-gritty of the training process. And believe me, it challenges some of the conventional wisdom in the field.
Okay.
And finally, we'll look at how all of that translates into performance. Because Falcon-H1 is setting new benchmarks, and often it's outperforming models that are much, much larger.
Get ready for some aha moments then, especially if you're interested in, the bleeding edge of efficient LLM design.
Definitely. Let's start with the basic challenge, right? The problem Falcon-H1 is trying to solve. For a long time, the dominant architecture has been the transformer. Super powerful, no doubt.
Right.
But its attention mechanism, that part that figures out which words are important, it suffers from this quadratic complexity problem.
Okay, quadratic complexity sounds technical. What does that actually mean in practice? Like, for the models themselves?
It basically means that as the input text gets longer, think a longer article or maybe a really long chat history,
Yeah.
the computation needed doesn't just scale linearly.
It gets worse than that.
Oh, yeah. If you double the sequence length, the compute cost quadruples. And you can imagine that becomes a massive bottleneck really quickly, especially for memory and computation when you're trying to handle really long contexts.
Right, like old documents or something.
Exactly. It's why long context models have historically been so resource hungry. You just hit this quadratic wall.
So hitting that wall is a real performance killer for long text. How does Falcon-H1 kind of elegantly sidestep this? What's their trick?
Well, their core innovation is this parallel hybrid architecture. So instead of just sticking with pure transformers or, the newer states-based models, SSMs like Mamba,
Oh, mix them.
they mix them, yeah. They combine both intelligently. The idea is to leverage the complementary strengths of each. So transformer attention is great at modeling those complex long-range connections between any two words.
Okay.
While SSMs, especially the Mamba 2 version they use, they're known for better long context memory and, crucially, linear computational scaling.
Ah, linear.
That's the key. That's the key. That linear scaling is what really breaks through the quadratic barrier. It's kind of like having two specialists working side by side, each doing the job they're best suited for.
Okay, so it's really trying to get the best of both worlds, strategically deployed. The paper talks about flexible attention and Mamba 2 heads running in parallel. Inside these hybrid mixer blocks, what's the big deal about running them side by side like that? Is that different from other hybrid models?
It is, yeah. Historically, a lot of hybrid designs you might have heard of, Jamba or Sama, they often used a sequential approach. So the output of one module, say attention, feeds directly into the next one, maybe the SSM.
Right, one after the other.
Exactly.
Yeah.
Falcon H1 flips that. They use a parallel design. Both the attention and the SSM modules get the same input at the same time.
Ah, okay.
Then their outputs are combined, concatenated, before the final step in that layer. And this parallel structure gives them this really unique flexibility.
Flexibility in what way?
In how they allocate resources.
Yeah.
They can independently change the number of internal channels. Think of it like processing capacity dedicated to attention, to the SSMs, and even to the MLP, the multi-layer perceptron, within each layer. It gives them really fine-grained control over how the model processes information.
That sounds like a powerful tuning knob, being able to adjust that mix in each layer. Did they actually experiment to find the best way to allocate those channels? Any surprises there?
Oh, absolutely. They did systematic studies on this, and the findings were, well, quite counterintuitive.
Really?
Yeah. They found that allocating more channels to the attention mechanism actually significantly degraded performance.
Wait, more attention made it worse. That sounds backwards compared to standard transformers.
Exactly. It goes against what you might expect, right? The best setup they found was a specific mix, which leaned more heavily on the SSM and MLP channels. It was roughly a 2 to 1 to 5 ratio for SSM to attention to MLP channels.
Huh.
It suggests that in this kind of hybrid setup, the SSMs are maybe doing more of the heavy lifting for certain tasks, and just throwing more attention at it might be redundant or even introduce noise or computational overhead. It's a really delicate balance they found.
That's a fascinating finding. More attention isn't always better in a hybrid. It really shows that the rules change when you mix architectures. Okay, let's dig a bit deeper into these state space models, the SSMs. Without getting lost in the math, can you give us kind of a high-level picture? How does an SSM sort of remember or integrate information as it reads? What are the main controls?
Sure. Think of an SSM having this internal hidden state. It's like a short-term memory that gets updated as it processes each word or token. They found sort of 4 key conceptual controls for this state.
Okay.
First, there's a forgetting factor. Let's call it A. It decides how much of the old memory to keep versus discard.
Makes sense.
Second, a write intensity, call it B. This controls how much of the current input word gets added into that memory.
Right.
Third, a reading projector C. This dictates how the current state of the memory is used to actually produce an output.
Okay, so writing, forgetting, reading.
And then there's a fourth, a direct connection D. This lets some part of the input bypass the memory state entirely and directly influence the output, like a shortcut.
Interesting.
And the time step parameter they mentioned, DT, that's pretty critical too. It dynamically adjusts both the writing B and forgetting A intensities, allowing the model to adapt its memory behavior based on the specific information it's seeing.
So these are kind of the internal knobs controlling memory and information flow. And the paper says Mamba 2 makes these controls input dependent. How does that make it more flexible than older SSM designs?
Right, that's a really key upgrade in Mamba 2. In older SSMs, those parameters, A, B, C, D, T, they were basically fixed values that were learned during training.
Static.
Static, exactly. Mamba 2 makes them dynamic. They get generated on the fly based on the current input token the model is looking at. It's like giving the model the ability to tweak its memory retention and how information flows based specifically on the nuances of this word in this context instead of using the same fixed rules for everything. That leads to much stronger expressivity.
That's clever. It adds a whole layer of adaptability. They also looked at head dimension. You can kind of think of that as the internal width or processing power of each little computing unit inside the model.
Right.
What did they learn there about performance and efficiency?
Yeah, head dimension is important. They found that larger head dimensions, say 64 or more, gave clear improvements in accuracy. But what was really interesting was the efficiency angle.
How so?
Smaller head dimensions, like below 32, actually reduced GPU utilization. They made the process less efficient. So it wasn't just bigger is better for accuracy. It was also about getting the most compute bang for your buck.
Ah, interesting. So going too small actually hurt efficiency.
Right. It provides a useful guideline for designing efficient SSMs. You need a certain head size, like 64 or above, to really keep the GPUs busy and get good accuracy.
Okay, finding that sweet spot. What about the balance they explored between state dimension and group count? How did those interact?
Okay, so state dimension, steed state, is basically the capacity of that internal SSM memory we talked about. Bigger D state usually means better accuracy, but it costs more computationally. Group count staying is another parameter.
Right.
Previous work wasn't totally clear on the trade-off. So Falcon-H1 did this detailed grid search, and they found validation accuracy went up almost exclusively with a larger state dimension, D state. Changing the group count barely made a difference.
Really? So it's all about the memory capacity?
Pretty much. It implies that for a given amount of compute or parameters, you're better off maximizing that state dimension and keeping the group count low. They eventually settled on ME1 and D-State 256 for most models as a good compromise, especially for handling longer sequences efficiently.
That makes sense. Another parameter they tweaked was the depth-wise causal 1D convolution kernel size. That sounds like something people usually just set and forget.
Often, yeah. It's frequently just fixed at size 4 in related work. But Falcon-H1 actually did an ablation study on this. They systematically varied the kernel size.
Did 4 turn out to be right?
It did. They found that a kernel size of exactly 4 minimized the validation loss. Both smaller kernels, like 2 or 3, and larger ones, like 5, actually degraded accuracy.
Huh. So the common wisdom was right, but they actually proved it was optimal for their setup.
Exactly. It just shows the level of detail they went into, optimizing even these seemingly minor hyperparameters. It wasn't just taken for granted.
Right. And finally, on the SSM parameters, chunk size, chunkus, how did that impact efficiency?
Okay, so the underlying SSM computations process the sequence in blocks, or chunks. The efficiency of this kernel scales with the chunk size, CS.
So bigger chunks are faster?
Up to a point. Very small chunks mean too many separate compute steps, and you don't keep the GPU busy. Very large chunks can cause memory problems, like running out of VRAM.
The classic trade-off.
Exactly. They found a kind of broad plateau, a sweet spot, where chunk sizes between 128 and 256 worked best. They balanced the overhead of launching many small computations against the memory pressure of large ones. For all their final models, they just fixed it at CS is equals 256.
Okay, 256 it is. Maximize throughput, stay stable. Good. Now, before we leave the core architecture, they mentioned something important for recurrent models like Mamba. Hidden state resetting. Sounds like it prevents memory bleed between documents. What's the issue and how did they solve it?
Yeah, this is a really crucial detail for training on concatenated documents, when you just stitch documents together into one long sequence for training.
Which is common practice.
Right. The hidden state, the internal memory from the end of document A, can leak into the processing of the beginning of document B. This causes semantic contamination. The model might mistakenly think something from the previous document is relevant to the new one.
I see. That could definitely mess things up. How do transformers handle that?
Transformers use attention masks. They basically tell the model, don't pay attention to tokens from the previous document.
Okay. And for Mamba?
For Mamba, they implemented this really clever trick. At the boundary between documents, they inject a large negative value into a specific SSM parameter related to the forgetting factor.
A large negative value.
Yeah. When this parameter goes through the math inside the SSM, it effectively forces the forgetting factor to become 0 instantly. It resets the hidden state, gives it amnesia about the previous document.
Wow. And that's efficient.
Incredibly efficient. It adds basically 0 extra compute or memory overhead. It just uses the existing mechanics in a smart way to ensure each document starts with a clean memory slate. No contamination.
That is a very elegant solution. Okay, fascinating stuff on the core architecture. Now let's shift to how Falcon-H1 challenged some, well, really conventional ideas in LM design. First up, ropey base frequency. Rotary positional embedding. They used a value of 1011. That sounds astronomically high. What's the reasoning?
It is unusually high, yeah. And it tackles a really common headache.
Yes.
Scaling LLMs to handle longer sequences than they were initially trained on.
Right, the context extension problem.
Exactly. Ropey works by assigning different rotation frequencies to different dimensions of the token embeddings, giving the model a sense of relative position. Conventionally, you use much smaller base frequencies, like 10,000.
Okay.
The problem is, when you want to extend the context lengths later, say during fine-tuning or at inference time, you usually have to mess with these frequencies. You use techniques like position interpolation or NTK-aware scaling.
Which can be complex and sometimes hurt performance.
Right. They can. It's like you're stretching or distorting the model's original sense of position that it learned during pre-training. You have to kind of awkwardly retune it.
So how does using a massive base frequency like 1011 avoid all that hassle?
The idea is, by using such a huge base frequency during the initial training, many of the potential rotational frequencies, corresponding to very long distances, are effectively left unused or unassigned, because the model never saw sequences that long.
Ah, so it reserves space.
Exactly. It leaves this vast positional memory untouched. Then, when you do want to increase the sequence length later, you don't need to modify ropey at all. You're just naturally using parts of the frequency spectrum that were implicitly kept free.
So no need for complex interpolation later on.
None. It dramatically simplifies sequence length extension, makes it much more robust, less likely to cause performance dips. It's like building in the potential for longer context right from the start.
That's actually brilliant. Very forward-thinking. The paper then asks this interesting question. Is this high base frequency only good for hybrid models like Falcon-H1, or could it work for pure transformers too? What are your thoughts on that?
That's a great question they posed, and yeah, it invites speculation. My hunch is that it might be particularly well suited to hybrid models.
Why?
Because in Falcon-H1, you have the Mamba component already doing a good job handling the short to medium range dependencies efficiently. This could free up the transformer's attention mechanism to really benefit from that very sparse high-frequency rope E for handling the truly long-range stuff without getting confused by local details.
Okay, so the Mamba part handles the close stuff. Attention handles the far stuff with this special ropey.
Potentially, yeah. For a pure transformer, it has to handle all ranges using attention and rope E. It might be more sensitive to needing those lower, more granular frequencies for shorter distances. But if this does generalize to pure transformers,
That would be huge.
it would be a significant simplification for building long context models. You could potentially ditch complex interpolation methods. It could really shift how people approach positional encoding, focusing more on smart parameter choices up front rather than complex fixes later.
Definitely something for the community to explore. Okay, another classic design choice. Width versus depth. Should models have more layers deep or more capacity per layer wide? What's the usual thinking, and how did Falcon-H1 tackle this?
Yeah, this is fundamental. Traditionally, depth is associated with learning hierarchical features, more complex reasoning. Each layer adds another transformation step. But it can increase latency, take longer to get an answer.
Right.
Width, on the other hand, means more processing power within each layer, more parallel computation. GPUs love this, doing big matrix math. It could be faster, but might not capture the same level of complex abstraction as depth.
So most models try to balance both, right? Scale them together.
Typically, yes. But Falcon-H1 decided to really isolate this. They fixed a parameter budget, 1.5 billion parameters, and then specifically varied the width and depth to see the trade-off.
Ah, a controlled experiment. What did they find?
The results were striking. For that fixed budget, greater depth consistently led to higher quality. Their deepest 1.5B variant, which had 87 layers, significantly outperformed wider, shallower models of the same size.
Wow.
And get this, it even matched or sometimes outperformed much larger reference models, like 3 billion or even 7 billion parameter models from other families.
Just by being deeper. That's incredible for efficiency. A smaller, deeper model beating bigger ones. But there must have been a catch.
There always is. The catch was training speed. While the deeper models were higher quality per parameter, their training throughput dropped by about 25–30%.
Slower to train, slower at inference probably too.
Exactly. So it's a clear trade-off, higher quality versus speed. Because this balance is still kind of underexplored, the Falcon-H1 team is actually releasing two 1.5B models, the standard one and this 1.5B deep version.
That's great to let people experiment.
Yeah, to encourage the community to dig into this depth-width question more.
That makes a lot of sense. And it begs the question, beyond just benchmark scores, when would you choose that deeper, maybe slower model over a wider, faster one? Are there specific use cases?
That's a really good point in thinking about applications. A deeper, narrower model, even if a bit slower, might be the winner for tasks demanding really complex, multi-step reasoning.
Like what?
Think advanced scientific problem solving, maybe generating really intricate code with complex logic, or understanding deeply nuanced language where relationships build up over many steps. The sequential nature of depth seems suited for that.
Okay.
Whereas a wider, shallower model might be better when you need raw speed and parallel processing for maybe simpler, more general tasks. High-volume text summarization, maybe. Or quick chatbot responses where latency is critical, but deep reasoning isn't the main goal.
So it really depends on the job. No single best shape.
Exactly. It highlights that the best architecture is really context-dependent.
Very insightful. Okay, let's switch gears now. Let's talk about the art of training, specifically the data and the dynamics behind training these models.
Right. Data, as always, is absolutely foundational. And for Falcon-H1, they really scaled up. Their pre-training corpus was over 20 teratokens. That's 20 trillion tokens.
Whoa.
Yeah, and they actually use up to 18 trillion of those for training. It's a massive amount of data. But critically, it wasn't just about the volume. They put a huge emphasis on the quality and the diversity of that data.
And the sources were incredibly varied, weren't they? Web data, multilingual stuff, code, math, even synthetic data. What kind of curation went into that?
A ton of curation. For English web data, they started with FineWeb, but applied really rigorous quality filtering, using smaller models essentially as judges to pick the good stuff.
Okay.
Multilingual data covered 17 languages from sources like Common Call, Wikipedia, Arcarc, Reddit, but with extensive filtering and deduplication.
Gotta clean it up.
Oh yeah. Code data was massive. 67 programming languages. They did file-level and repository-level analysis, used quality classifiers, redacted PII. Math data mixed open-source sets with their own crawled data. but they were super careful to decontaminate it from common benchmarks to ensure fair evaluation later.
That decontamination step is important. It shows real rigor. And what about synthetic data? That's a hot topic. How did they approach it?
They used a hybrid strategy. They did use some external synthetic data sets like Nemotron CC and Cosmopedia, but their main focus was on in-house rewriting of curated raw data.
Rewriting, how does that work?
They took good quality sources, web text, code, books, Wikipedia, Arpertiva, math, and then used various models to basically improve them. Enhance the writing style, boost the knowledge density, filter out redundant bits, and apply iterative quality control.
So using AI to make the data better for training AI.
Pretty much. One interesting thing was generating synthetic textbooks based on Wikipedia topic structures. They covered like 30,000 topics with structured content, examples, exercises, trying to create really dense structured knowledge sources beyond just simple Q&A pairs.
That sounds way more sophisticated than just generating question-answer pairs, really focusing on structured knowledge.
Okay.
This focus on quality leads into their overall data strategy, which had some pretty unconventional elements. Let's start with data validation. Why on earth did they train multiple small 0.5B models from scratch just to check data sources? Isn't that super expensive?
It is computationally expensive, yes. But their argument is that this approach gives stronger, more interpretable signals about the quality of individual data sources or how different combinations perform.
Compared to what?
Compared to the more common practice of just tweaking the data mixture while you're training one big model, especially during the learning rate decay phase, they argue that the approach often gives unclear or confounded results. You don't know if a change was due to the data or the learning dynamics.
Ah, I see. Too many variables changing at once.
Exactly. By training separate small models on specific data subsets, they could isolate the effect of that data. They could precisely evaluate its quality and how it interacted with other sources for specific tasks. Once validated this way, the data was either approved for the big models, kept, or adjusted. It's a very systematic, almost scientific method for quality control.
That's a huge commitment, but I can see the logic. Rigorous control.
They also mentioned deterministic beta loading and checkpointing. What are the practical benefits of that? Sounds like it helps with stability.
It offers several big advantages, especially at scale. First, determinism means every training run behaves identically if you give it the same starting point. That's crucial for doing reliable ablation studies or tuning hyperparameters. You can actually trust your comparisons.
Right, apples to apples. Exactly. Second, it allows for really flexible, continual pre-training. They could precisely coordinate model checkpoints with data checkpoints across different sources and stages very smoothly. This level of control really contributes to training stability and reproducibility, which you absolutely need when you're training models this big.
Sounds like an engineer's dream for managing large training runs.
Right.
And speaking of data mixtures, they iteratively refined them. You mentioned they significantly reduced raw web data for the bigger models, favoring rewritten and knowledge-intensive stuff. Doesn't that go against the grain? Isn't more web data usually seen as good for generalization?
It does seem counterintuitive, yeah. The standard worry is that if you cut back too much on broad web data, the model might lose general knowledge or struggle to generalize. However, Falcon-H1 found this concern to be, in their words, somewhat overstated. Yeah. They found that even popular, heavily filtered web data sets often have relatively low knowledge density. By using their own high-quality, knowledge-dense, rewritten web samples, they could cut the proportion of raw web data down to around 15% for the biggest models, and they didn't see a hit to generalization or knowledge diversity.
So quality over quantity, even for web data.
It strongly suggests that yes, especially if you have good rewriting capabilities, the density and quality of information seem much more important than just raw volume from the web, at least beyond a certain point.
That's a really important finding. It suggests you could train powerful models with less total data if that data is incredibly good. Now, they also challenged another common practice, single epoch training. People do that to avoid memorization, right? But Falcon-H1 argues memorization is overstated, and there's a memorization window allowing data reuse. Can you break that down?
This is a pretty significant claim they're making. The traditional wisdom is train for one epoch only on your massive data set to prevent the model just memorizing samples and failing on new stuff.
Right, overfitting, essentially.
Right. But Falcon-H1 did some empirical investigation. They tried to estimate what they called the memorization window, basically, how long the model strongly remembers specific training examples it just saw. Their analysis, looking at training loss on tokens seen at different points in the past, suggested that for these very large models trained on trillions of tokens, you can actually reuse high-quality data multiple times without seriously hurting generalization.
So you can show it the good stuff more than once.
Their argument is yes, within limits. The window where harmful memorization might dominate is maybe smaller than commonly assumed in these massive scale regimes. It challenges the idea that any data reuse is automatically bad. It means you might be able to get more mileage out of your best, highest quality data by carefully reusing it.
That's huge, especially since truly high-quality data is so hard to get. Being
Hmm.
able to reuse it is a big win. Okay, then they did something that sounds completely backwards, an anti-curriculum approach. What on earth is that, and why did they say it worked better?
Yeah, anti-curriculum sounds weird, right? It means they fed the model data of all complexity levels, from simple sentences to super complex math problems, right from the very beginning of training.
Instead of starting easy and getting harder,
Exactly. That's conventional curriculum learning starts simple, gradually introduce complexity. The anti-curriculum approach is full immersion from day one. Their hypothesis was that this forces the model to develop the necessary internal machinery for handling complex tasks much earlier in the training process.
and did it work?
Their experiments showed it consistently outperformed the traditional curriculum strategies, provided they had enough high-quality complex data available from the start.
So throwing it in the deep end actually made it learn better overall. That's
Yeah.
wild. What kind of internal features do you think that forces the model to develop earlier on? The paper doesn't really speculate, does it?
It doesn't go deep into the why, but that's a great question to ponder, I guess. By seeing complex stuff early, the model might be forced to build more robust, more generalizable feature extractors right away. Instead of learning simple patterns and then struggling to adapt them later, it has to build representations capable of handling complexity from the start.
Like building a stronger foundation.
Exactly. Maybe it develops richer internal ways to represent logical steps or symbolic relationships or hierarchical structures much earlier, and that stronger foundation then benefits all tasks, even the simpler ones it sees later or concurrently. It's like forcing a student to grapple with fundamental theorems early on, making them build a solid conceptual framework rather than just memorizing isolated facts. Could lead to better transfer learning down the line.
That's a really interesting hypothesis. Okay, last point on data strategy. Their long context training. How did they structure that? Was it long context from the start?
No, they use a staged approach. Pre-training mostly happened at 8K and then 16K token context windows. The smallest 0.5B model used 4K. The key thing is that the extension to the really long contexts, 32K, 128K, all the way up to 256K, happened after the main learning rate decay phase was finished.
Why after? Does that affect performance?
They checked that. Empirically, they found no significant performance difference compared to extending the context before the decay. But doing it after was substantially more compute efficient.
Ah, because training on long sequences is slower.
Exactly. So it's a pragmatic choice to save compute resources without sacrificing final quality. Train the bulk of the model on shorter, faster contexts, then extend it later when the learning rate is already low.
Makes sense. Okay, that covers the data side. Now let's get into the nitty-gritty of optimization, the training dynamics. They mentioned running into severe loss spikes early on. That sounds painful. What caused them, and how did they fix it?
Oh, loss spikes are a nightmare in large model training. They can totally derail experiments, force you to use lower, safer learning rates that might not be optimal. Falcon-H1 saw these too.
What was the cause? Was it the hybrid nature?
They diagnosed that the spikes were present even when training pure Mamba 2 models, so the SSM pathway was definitely involved. More specifically, they found that scaling the model width, particularly having a larger number of SSM heads, seemed to be a primary driver.
So wider models were more prone to spikes?
It seems so. Their hypothesis was that certain internal parameters within the SSMs, especially when there were many heads, could create sort of conflicting or antagonistic signals, causing the learning process to become unstable and overshoot, leading to the spike.
Okay, so it's a dynamic related to the SSMs and width. How did they fix it? Did they have to do things like skip batches?
They explored a few things, but they found a more elegant solution. They identified specific parameters within the SSM activation function, DT, that seemed problematic. By carefully clipping the positive values of this parameter, or using a soft attenuation factor for its activation, they essentially tamed these potentially explosive internal signals.
Ah, so they addressed the root cause within the math.
Exactly. And this fix completely removed the spikes, which then allowed them to train successfully at higher, more optimal learning rates without instability. It made the whole process much smoother and more robust.
That's a much cleaner solution than just reacting to spikes after they happen. Okay, then they introduce these interesting concepts. Effective learning rate, ELR, and effective weight decay, EWD. Sound like they're rethinking how learning rate and weight decay actually work together.
Yeah, this is digging into the optimization theory a bit. Conventionally, we think, learning rate controls step size, weight decay shrinks parameters to prevent overfitting. Simple enough. But they noticed something weird in their experiments. Changing the weight decay value often had a very similar effect on the training loss curve as changing the learning rate. The two seemed intertwined.
Huh. They weren't independent controls.
Not entirely, it seemed. So they proposed these new concepts. Effective learning rate, ELR, is defined as squirt eta lambda, where eta is LR and lambda is WD. This ELR, they argue, primarily governs the noise level or the fluctuations during training.
Okay. And effective weight decay.
Effective weight decay, EWD, is squirt lambda eta. This EWD, they found, primarily determines the final size or norm of the model's parameters.
So they're trying to disentangle the effects.
Exactly. And they found these two effective parameters operate in a kind of log-scale orthogonal way, meaning you can adjust one without drastically affecting the optimal setting of the other, at least more so than the original LR and WD. This potentially simplifies tuning because you can think about controlling the noise level, ELR, and the parameter size, EWD, somewhat independently.
That's a neat theoretical insight. Makes tuning potentially less of a black art. Now, maximal update parameterization, or CP, that's a known technique, but Falcon-H1 adapted it with tunable multipliers. How does that work, and why is it important for training a whole family of models?
Right. Peaky is fundamentally about making sure that as you scale up a model, make it wider, it actually learns better features, not just redundant ones. It ensures feature learning doesn't break its scale. A key practical benefit is often zero-shot hyperparameter transfer, tuning on a small model and having those settings work for a large one.
Okay. How did Falcon-H1 apply it?
The standard OMP involves specific scaling rules for initialization, learning rate, and weight decay based on model width. Falcon-H1 did something different. Instead of scaling the global learning rate or weight decay, they relocated the AP scaling inside the network, applying it directly to the multipliers of various internal operations.
Which inside the network?
Yeah. They identified 35 distinct forward multipliers things controlling the strengths of signals from embeddings, MLPs, attention, SSMs, gates, internal SSM parameters like B, C, D, T, etc. They applied the AP scaling rules to these multipliers.
And what's the advantage of doing it that way?
The big advantage is that now the same global learning rate and weight decay can be used effectively across their entire family of models, from the tiny 0.5B up to the 34B. All the necessary scaling adjustments for different model sizes happen internally via these preset multipliers. This greatly simplifies transfer tuning and continuous pre-training across the family.
That makes scaling experiments much easier. But wait, 35 tunable multipliers? That sounds like a nightmare to tune initially. Did they tune all 35?
That's a really astute point. The paper mentions they performed a sensitivity analysis on these multipliers and found that fine-tuning them individually yielded significant performance improvement. Tuning 35 hyperparameters is indeed a massive search problem.
How would they even approach that?
They don't detail the exact method, but likely involve sophisticated hyperparameter optimization techniques, possibly automated searches, maybe informed by sensitivity analysis to focus on the most impactful ones. It highlights the sheer amount of careful engineering and computational effort that went into optimizing Falcon-H1. Making this kind of granular tuning more accessible would certainly be valuable for the wider community.
No kidding. Okay, last few bits on training dynamics. Batch scaling, ramp up, warm up. Anything particularly noteworthy there?
These are pretty standard practices, but they did have specific findings. For batch scaling with the Atom Optimizer, they used a square root scaling rule, eta nu the iteref squirt, batch new batch ref. They found this worked well, preserving optimal learning dynamics when they changed batch sizes.
Okay, what about ramp up? That's increasing batch size over time.
Yeah, they linearly increased batch size over the first 50 gigatokens.
Cool.
Interestingly, they found that ramp up with batch scaling, while initially performing slightly worse than no scaling, eventually overtook it and led to a better final loss.
So guiding it to a better spot in the parameter space.
That was their interpretation, yes. It suggests the scaling helps guide the trajectory early on. And for warm-up, the initial linear increase in learning rate, they found the duration mattered quite a bit. Even a short optimal warm-up, around zero point 0.1 gigatokens, had a long-lasting positive impact on the stability and final value of the loss curve.
So even these seemingly small details add up. It's all about careful tuning at scale. Okay, that brings us to the incredible engineering needed to actually do all this training. Let's talk about Mambotron.
Right. Mambotron is their in-house distributed training framework. It's an evolution of their previous system, Gigatron, but specifically optimized for this new hybrid Mamba transformer architecture.
And it uses the standard types of parallelism.
It builds on the standard 3D parallelism. Data parallelism, splitting batches across GPUs, tensor parallelism, splitting layer tensors across GPUs, and pipeline parallelism, splitting layers sequentially across GPUs. But the real innovation is in how they adapted things for the hybrid model, especially for long sequences.
Okay, what were the key innovations there? First was Context Parallelism, CP. How does that let them handle sequences up to 256,000 tokens long?
Context parallelism is essential for ultra-long sequences. The basic idea is to shard each sequence horizontally across different GPUs. So instead of one GPU needing to hold the entire 256K sequence, each GPU only holds a smaller chunk, say 8K tokens. This keeps the memory usage per GPU flat, even as the total sequence length grows massively.
Okay, but how do they handle operations that need information across chunks, like attention or the SSM state?
Good question. For the self-attention parts, they reuse a technique called ring attention. Each GPU computes attention for its local chunk, but then they efficiently pass the necessary key and value tensors around in a ring between GPUs. This lets them compute the full attention scores without any single GPU needing the entire sequence's KV cache. Memory scales linearly per GPU, like OQN, where Q is sequence length and N is number of GPUs.
Clever. And for the Mamba SSM parts?
For the SSMs, they use a chunk-wise state passing schedule. Each GPU processes its local chunk independently and then just passes the final hidden state of its chunk to the next GPU in the sequence. That next GPU uses it as the starting state for its chunk. This also scales very well. And even the causal convolution step before the SSM is split, similarly, passing just a few necessary time steps between neighbors.
It sounds like a very carefully choreographed dance of data between GPUs to keep memory manageable. Okay, the second big innovation was Mixer Parallelism. MP, that sounds completely new. What does it do?
Mixer parallelism is specifically designed for their parallel hybrid architecture, where you have attention heads and Mamba heads operating concurrently within the same block. MP takes the group of GPUs normally used for tensor parallelism and splits that group into two subgroups.
Okay.
One subgroup becomes dedicated solely to computing the Mamba operations for that block, while the other subgroup simultaneously computes the attention operations. They run in parallel. Then there's a synchronization step to combine their outputs before moving to the next part of the layer, like the MLP.
So it parallelizes the two different mixer types themselves. What's the difference between the naive and interleaved versions they mention?
Naive MP just assigns fixed groups of GPUs, say GPUs 0, 3 always do Mamba, GPUs 4, 7 always do attention for every layer. Interleaved MP is smarter. It alternates the assignments layer by layer or block by block. So maybe on layer 1, GPUs 0, 3 do Mamba, but on layer 2, they do attention, and GPUs 4, 7 do Mamba. This helps balance the computational load better, as attention and Mamba might have slightly different costs.
Right, load balancing. And did this mixer parallelism actually speed things up in practice for training?
Oh yes, they tested it on a 2B parameter hybrid model. The interleaved mixer parallelism achieved a really substantial 1.43x speedup compared to not using MP at all.
Wow, 43% faster training just from that parallelization strategy.
Exactly. It shows that cleverly distributing the work between the parallel attention and Mamba components can significantly boost training throughput. Faster training, lower costs. That's a big win for training. But they also look at inference efficiency with MP, and there was a catch, right? How did it perform there?
Right, the inference story was more nuanced. They found that mixer parallelism does significantly speed up inference, but primarily in low latency scenarios. Think small batch sizes, generating only short sequences of text.
Okay, what happens with bigger batches or longer generation?
The advantage diminishes, or can even reverse. For large batches or generating very long sequences, the baseline approach, without MP, sometimes became faster again.
Huh. Why would that be? Isn't the hybrid architecture supposed to be great for long contexts?
It is, theoretically, but this finding points towards the implementation details. It suggests that the current software optimizations for SSMs within inference frameworks like VLLM are just less mature than the years of optimization that have gone into attention mechanisms.
So the software hasn't caught up with the hardware and architecture potential for SSMs yet. That seems to be the implication. The paper explicitly calls this out, framing it as a promising direction for future work. They're basically inviting the community to help optimize SSM inference implementations to fully unlock the theoretical benefits, especially for high-throughput, long-sequence generation.
That's a really clear call to action for inference framework developers then. Close that gap. Okay, let's move on to the final stages. Post-training and evaluation. How did they fine-tune these models after pre-training?
They used a pretty standard but robust two-stage process. First was supervised fine-tuning, SFT. This is where the model learns to follow instructions and generate desired outputs based on curated examples.
Okay.
Second was direct preference optimization, DPO. This uses datasets of paired responses, where one is preferred over the other, to further align the model's behavior with human preferences, making it more helpful and harmless.
And they really focused on improving the data for this stage, right?
Absolutely. They significantly expanded and improved the quality of their SFT and DPO data compared to earlier Falcon models. The focus was clearly on enabling complex reasoning, math and science problem solving, better instruction following, and even adding capabilities like function calling.
Any specifics on the SFT stage? You mentioned long context earlier.
Yeah, the SFT had two phases. A main stage trained for 3 gigatokens using a 16K context length. Then, a dedicated long context SFT stage, also for 3 gigatokens, but extending the context up to 128K. They used a specific learning rate schedule, warm-up stable decay, and that square root batch scaling again to handle different model sizes effectively.
Okay. And for DPO, any interesting findings there?
They used a mix of open-source preference datasets and their own internal ones, building on the LNAI OpenInstruct framework. The surprising empirical finding was about how long to run DPO. They found that stopping after approximately 1 epoch actually gave better results than running for the full 2 epochs suggested by the schedule.
Again, less is more sometimes. Training for too long on preference data might not be optimal.
It seems so, at least for their setup. It might start to overfit the preference data or degrade other capabilities. It's another example of careful empirical tuning being crucial.
Definitely. Okay, so after all this training and tuning, the evaluation, how thoroughly did they benchmark these Falcon-H1 models?
Yeah. Very thoroughly. They benchmarked against a whole suite of leading open models, Qwen, Gemma, Llama, etc., using well-established open-source evaluation harnesses like Elm, Evil Harness, EvalCami, EvalPlus, Helmet.
And they focused on fair comparisons.
Yes, they emphasized standardization.
Yeah.
Used a consistent Docker environment, made sure to disable specific features like Qwen 3's thinking mode that could inflate scores, standardized generation settings for math benchmarks, use specific post-processing like Math Verify. It looks like a rigorous and fair comparison setup.
Excellent. Let's get to the results. Starting with the base models, the ones just after pre-training, how did the smallest, the 0.5B base, do?
The Falcon-H1 0.5B base really set a new bar for models under 1 billion parameters. Despite its size, it led on basically all the math, science, and code benchmarks they tested, often by significant margins. For example, GSM-8K math reasoning was over 60%. Way ahead of competitors. It also topped complex reasoning tasks.
So strong on reasoning even at that tiny scale.
Exactly. While bigger models in its class might have edged it out on simpler common sense stuff, its performance showed that even a 0.5B model can tackle complex tasks surprisingly well if designed right.
That's really encouraging for small, efficient models. What about the 1.5B deep base? Did that depth really pay off?
It absolutely did. The 1.5B deep variant clearly established itself as state-of-the-art in its class. It wasn't just better than other 1.5B models. It was often competitive with or even beating leading 7B to 10B models from other families.
Wow.
And the benefit of depth was especially clear on reasoning-heavy tasks. It significantly outperformed its shallower 1.5B counterpart on science and math benchmarks. It really validates their architectural choice for boosting reasoning.
Depth matters. Okay, moving up to the 3B base model.
The 3B base showed remarkable training efficiency. Remember, it was trained on way less data than some competitors, like 10x less in some cases. Despite that, it delivered highly competitive results, achieving state-of-the-art scores in advanced math reasoning, Math-VL5, and multilingual tasks, MGSM. And critically, its performance curves suggested it still had room to improve with more training.
So punching well above its weight, data-wise. That points to the architecture and data quality again. How about the 7B base?
Falcon-H1 7B base set a new overall state-of-the-art for 7D models. Its leadership was particularly strong in complex, knowledge-intensive areas. Top scores on MMLU, advanced math, scientific QA, GPQA. It also excelled in code generation and multilingual math, While competitors might win on specific narrow tasks, the 7B's broad strength, especially in reasoning, made it stand out.
A very strong all-rounder at 7B. And the flagship, the 34B base, how did it measure up against models that are often much bigger, like 70B?
The 34B base delivered truly state-of-the-art performance with incredible parameter efficiency. It consistently challenged and frequently outperformed models up to 70B parameters. It even competed well against some much larger mixture of experts models.
Seriously.
Yeah, top scores on challenging reasoning benchmarks like BBH, advanced math, scientific QA, and across all code generation tasks. While maybe giant models still hold an edge in sheer breadth of general knowledge, the Falcon-H1 34B was often number 2 and led decisively in complex reasoning and coding. It positions it as a very compelling, efficient alternative to much larger models for those demanding applications.
That's incredibly impressive. Consistent SOTA performance, amazing efficiency, leadership and reasoning across the board for the base models. Okay, now let's look at the instruct models, the ones tuned for chat and following instructions. How did the little 0.5B instruct perform?
The 0.5B instruct mirrored the base model's success. New state-of-the-art for sub-1B instruct models. Its dominance was most striking in math, where it swept all the benchmarks, showing it could follow complex problem-solving instructions remarkably well for its size. It was also top in science and code. And crucially, it scored highest on instruction-following benchmarks like IFEVL, confirming its ability to adhere precisely to complex instructions, maybe even more so than just general chit-chat at this scale.
Amazing capability for such a tiny footprint. And the 1.5B instruct models, especially the deep one.
At the 1.5B scale, both instruct models were dominant, setting new SOTA benchmarks. The 1.5B deep instruct, though, was in a league of its own. It achieved comprehensive leadership across almost every category: general, math, science, code, multilingual. Its performance level was genuinely competitive with state-of-the-art 7B instruct models.
A 1.5B model competing with 7B models?
Yes. The gap was especially wide in complex reasoning tasks. It really shows the power of that deep architecture combined with their effective instruction tuning pipeline.
Incredible scaling. Moving up, the 3B instruct.
The Falcon-H1 3B instruct emerged as a top performer, very versatile. It led on most general knowledge benchmarks, dominated science, and got state-of-the-art scores on instruction following, IFEVL, and conversational ability, MD-Bench. It also showed clear advantages in code generation and multilingual tasks, a really strong, well-rounded model in its class.
And the 7B instruct, how did that compare?
The 7B instruct was highly competitive, notably outperforming larger models like Gemma 312B on most benchmarks they showed. It excelled in knowledge-intensive areas, leading all science benchmarks in key general reasoning tasks. Top scores in human-evil code generation, and led across all multilingual benchmarks too. A very capable and versatile model for sophisticated instruction-driven tasks.
Finally, the big one, Falcon-H1 34B instruct. How did its parameter efficiency hold up in the instruct setting?
It held up extremely well. The 34B instruct consistently competed with and often beat models twice its size, like 70B instruct models. Its main strengths were deep knowledge and reasoning. It led the entire science category in key general reasoning benchmarks like HelloSwag. It also got a top score on MT-Bench, confirming strong conversational skills. While the very largest models might pull ahead on some math or coding benchmarks due to sheer scale, the 34B's efficiency delivered SOTA results in science and general reasoning, making it a powerful, cost-effective option for knowledge-heavy applications.
And they specifically highlighted its long context abilities thanks to Mamba. What was the standout achievement there?
The really unique achievement for the 34B instruct was getting the top score on a retrieval augmented generation RAG benchmark using a massive 131,000 token context.
RAG at 131K tokens.
Yeah, this shows a superior ability to actually find and synthesize information from a huge set of retrieved documents, which is exactly what you need for practical RH systems dealing with large knowledge bases.
That's more practical than just recalling a single fact from a long text.
Exactly. While some larger models might have slightly better pure recall on needle-in-a-haystack tasks at extreme lengths, Falcon-H1 argued this might be due to data composition differences during training, not fundamental architectural limits. And even with that nuance, it still broadly outperformed the much larger Qwen 2.5 70B instruct across most long-context tasks they've tested.
That's a very strong showing for real-world, long-context use cases like RAG.
Okay, wrapping up, let's look at the future of efficient LLMs, starting with their direct efficiency comparison. How did Falcon-H1 actually compare in terms of speed?
They did a direct comparison of the Falcon-H1 34B against a similarly sized transformer model, Qwen 2.532b, on H100 GPUs using the VLLM inference server. They measured throughput, how many tokens per second they could process for input, prefill, and generate for output generation.
And the results.
The key finding was dramatic. While the transformer had a slight edge for very short context lengths, as soon as the context got longer, Falcon-H1 34B became significantly more efficient.
How much worth? At the longest sequences they tested, Falcon-H1 achieved up to a 4x improvement in input throughput and an incredible 8x speedup in output generation throughput.
8 times faster generation at long context.
Yes. It really underscores the efficiency benefits of the hybrid Mamba architecture for use cases involving long documents, extensive chat history, or complex RAG.
But why was the transformer slightly faster at the very short context? We touched on this.
Right. The paper attributes this to the maturity of optimizations. Attention mechanisms in frameworks like VLLM have been heavily optimized over years. State space model implementations are newer and haven't received that same level of intense optimization yet.
So it's a software maturity gap, not a fundamental limitation of SSMs.
That's the argument. And as we said, they explicitly frame this as a promising direction for future work, a call for the community to optimize SSM inference. The potential is there for SSM-based models to be faster across the board once the software catches up.
That's a clear challenge and opportunity. And speaking of the community, how easy is it for people to actually get their hands on and use these models?
They've clearly prioritized accessibility. Falcon-H1 is deeply integrated across the open source AI ecosystem. You can find it in general tools like VLLM and Hugging Face, fine-tuning libraries like Llama Factory and Unsloth, and tons of local deployment options. Llama.cpp, LM Studio, Ollama, Apple MLX support.
So you can run it pretty much anywhere.
Pretty much, from your own laptop to cloud deployments using tools like SkyPilot, plus quantization support with AutoGPT-Q to make them smaller and faster. They've made it very easy for developers and researchers to start experimenting and building.
That commitment to open source and accessibility is fantastic. Okay, so let's try to summarize the core message here.
The core message is that the Falcon-H1 series really redefines the balance between performance and efficiency. Its innovative hybrid Mamba transformer architecture allows it to achieve state-of-the-art results, often beating much larger models, while using significantly less training data and offering dramatically faster inference, especially in long context scenarios.
And the ultimate value proposition for you, our listener.
The value is that these models provide a powerful, yet efficient and versatile foundation for building sophisticated AI applications. Whether you were working on edge devices or large cloud systems, Falcon-H1 offers top-tier capabilities without necessarily needing massive, resource-hungry models. It challenges the idea that bigger is always better.
And what's next? Where does the research go from here, according to the paper?
They outline 3 main directions. 1. Keep improving the data broader, more diverse, higher quality data sets. 2. Continue innovating on architecture and algorithms, things like knowledge compression, scaling context beyond the current 256K limit. 3. Strategic scaling, not just making models bigger, but scaling in ways that specifically deepen core reasoning capabilities.
So pushing boundaries in intelligence and efficiency, not just raw size.
Exactly.
Okay, so let's reinforce those key takeaways for everyone. Falcon-H1 really stands out. You've got the smart hybrid architecture blending transformers and Mamba. You've got meticulous data and training strategies that squeeze out efficiency, like the anti-curriculum and careful data reuse. And you've got, frankly, impressive benchmark performance across complex tasks, often for models much smaller and more resource-friendly than the competition. It really feels like a game changer for making high-performance AI more accessible.
I agree. It's a very significant contribution.
And it leaves us with a provocative thought, doesn't it? As we've seen today, maybe the future of LLMs isn't just this relentless race to bigger and bigger parameter counts. What if the truly transformative breakthroughs come from smarter architectures, more efficient designs, better data strategies? Could we see powerful AI running effectively on devices we never imagined? What are the key inference and optimization innovations, like the ones Falcon-H1 calls for with SSMs, that will unlock that next wave beyond just the cloud? What really stands out to you listening now about this fascinating balance between brute force scale and intelligent, efficient design?